Okay, so welcome to the last session of this day. And now we have Elkida video, more or less, about distributed edge coloring. Thanks.
Thank you, Ami. This presentation would be about the distributed edge coloring problem. And this is a joint work with Fabian Kuhn and Dennis Olivetti. In the distributed setting, there are 4 classical symmetry breaking problems that have been extensively studied. And these problems are maximal independent set, maximal matching, delta +1 vertex coloring, and 2 delta -1 edge coloring. And we know that there are some relations between these problems. For example, we know that if we have an algorithm for solving delta +1 vertex coloring, we can use it on the line graph and obtain a solution for the 2 delta -1 edge coloring. Also, we know that, for example, if we have an algorithm for the maximal independent set problem, we can use it to solve the delta +1 vertex coloring problem. This reduction is not as trivial as the first one, but still we know how to do that. And all these problems can be easily solved with a greedy algorithm in the centralized setting, while in the distributed setting, they are somewhat challenging. So over the years, researchers have studied the locality of these problems. And what do I mean by the locality of these problems is the following. Since the 80s, we know from linear that for solving these problems, we need to spend omega of log star of n rounds. And the question is, if we want to be optimal as a function of n, what is the right complexity as a function of delta, where delta is the maximum degree of the graph? And in this work, we have studied the locality of the 2 delta -1 edge coloring problem. And we show a deterministic algorithm for solving this problem in the classical local model of the distributed computing. And over the years, we have learned a lot about these problems. For example, from some time now, we knew that maximal independent set and maximal matching can be solved in order of delta plus log star of n rounds. And since last year, we know that this is essentially optimal, meaning that if we want to be optimal as a function of n, we must spend linear in delta. And on the other hand, if we want to spend sublinear in delta, we must spend at least log n over log n with deterministic algorithms. While on the other hand, the delta +1 vertex coloring problem, we know that it is strictly easier than these other 2 problems, because we know that we can solve it in sublinear in delta plus log star n rounds. And for the 2 delta -1 edge coloring, very recently Kuhn have showed that we can solve it in subpolynomial in delta plus log star n rounds. And for vertex coloring and edge coloring, the only lower bound that we know is the linear lower bound that we know since the 80s, that is omega of log star of n. And we do not know any lower bound as a function of delta. And this is a major open question. And in this work, we show that actually 2 delta -1 edge coloring can be solved in time quasi-polylogarithmic in delta plus order of log star of n deterministic rounds in the local model. And in order to show this, we actually prove something stronger. We show that degree +1 least edge coloring can be solved in time quasi-polylogarithmic in delta. But let's see what this problem is. In the least edge coloring problem, each edge is given in input a list of colors, and we want to produce a proper edge coloring of the graph such that each list gets a color that is, each edge gets a color that is in its list. And in the degree +1 least edge coloring problem, the list of an edge must be of size at least degree of the edge +1, where with the degree of an edge, I mean the degree that it has on the line graph. And it is not difficult to see that 2 delta -1 edge coloring is actually a special case of the degree +1 least edge coloring, where all edges are given in input the same list of colors of 2 delta -1, of size 2 delta -1. So the same list of 2 delta -1 colors. And I conclude with some open questions. on the upper bound side, we have shown that 2 delta minus 1 edge coloring can be solved in time quasi-polylogarithmic in delta plus order of log star of n. And this really doesn't seem the right answer for this problem. So a natural question is, can we solve this problem in polylog delta plus order of log star of n rounds? And on the lower bound side, as already mentioned before, the only lower bound that we know is of omega of log star of n. And a concrete question can be the following. Can we show, for example, that 2 delta minus 1 edge coloring cannot be solved in little o of log delta plus order of log star n rounds? Thank you, and for more details, please see the longer version of the talk on YouTube.
Thank you, Alkida. Questions?
Yes, I have a question, Alkida. Hi.
Yeah.
Thanks for the talk. If you allow slightly more colors, can you do much faster?
If you allow delta to the 1 plus epsilon colors, for example, you can do this in order of log delta plus log star n, and this is a known result by Barenboim and Elkin, if I'm not mistaken.
Okay, thanks.
There is a long line of research, and people have studied this problem in many variants, using more or less colors, and yes.
Thanks.
Thank you for the question.
Other questions?
Hi. Yeah, I already wrote it on Slack, but on this chat. But I'm wondering, do you have now any reasons to expect that this log of delta would be the right bound?
Right. You mean for the upper bound? I mean, yeah. I don't have any strong opinion on that, but I would be very surprised if one can solve this problem really in little o of log delta plus log star of n. But I don't have any strong reason why. But I would be really surprised. But
for instance, your recent work, it's not giving any, let's say, further evidence that log delta might be the right bound or something like this.
Unfortunately, no.
Okay, thanks.
Thank you.
Okay, anyone else? Okay, so thanks again, Alkida, and we'll move to the next speaker.
Okay.
In Leitersdorf. Oh, thank you. And you, just a minute. Yeah, you can. I mean, you can start. Thank you very much.
Okay, thank you, Amy. So I'll be giving a talk on joint work with Karen and Francois on distributed listing of cliques. So our paper is in the realm of subgraph existence problems, where in these problems, we're given an input graph and a subgraph. And we're asked to detect certain places in the input graph where the subgraph exists. In the most simple version, we're simply asked to determine if the subgraph exists anywhere in the input graph. In a more complicated version, one is asked to give an exact count of how many instances of the subgraph appear in the input graph. And in the most difficult version that's usually considered, one is asked to give an exact list of all the instances of the subgraph in the input graph. So in our work, we talk about listing cliques. Cliques, that is, small subgraphs where every node is connected to every other node. Now this problem has been heavily researched in distributed settings already. So in the congested clique, it's been known for a long time now that it's possible to solve this problem optimally for cliques of any size. Later on, it was shown that it's possible to solve counting for triangles for K3 much, much faster, but it was also shown that showing lower bounds for this problem is very difficult in the congested clique. In parallel, works developed the approach of using sparse listing. That is, if the input graph itself is sparse, can we perform the listing operation faster? And for K3, this problem was solved. One of our results in this paper is solving this problem for general KP. Basically for all cliques, solving it in optimal number of rounds, even depending on the sparsity of the input graph itself in the congested clique. Now, following the congested clique model, many researchers looked on how to do the same thing in the congest model. And so they started with the problem of K3 with triangles. And a beautiful line of works managed to show over the years how to optimally list all triangles in the congest model, while the detection problem is still open, and the only lower bounds we know in that section is that we need more than one round to solve this problem in congest. Following the solutions for K3 and congest, the question of what happens when we go into bigger cliques, K4, K5, and even bigger than that, started coming up. And so recently, the first work showed two algorithms for K4 and K5, which produced sublinear results for the listing problem. In this work, our main result is a single algorithm which achieves sublinear listing for cliques of all sizes in the congest model. Now, after this work, we collaborated with Yijun Chang, and we have an unpublished work which solves this problem optimally for cliques of all sizes. And so just a little bit about how we do this. So a common thread along all the works in congest in this setting is using expander decompositions, where expander decompositions take the graph in congest and basically break it up into small clusters, where every cluster is very similar to the congested clique, and so congested clique algorithms can be run inside the clusters. Now, we also use this expander decomposition as a black box, but the way we do this is with two iterative approaches which invoke the expander decomposition with a wide range of parameters. So we look for clusters which are very, very huge, clusters which can be even linear in size, and also for very tiny clusters. And we have algorithms which adapt to the sizes of the clusters in order to better and more efficiently perform the listing with these different types of clusters. Now, the overall approach that we take is basically split into two cases. The first is that the big difference between congest and congested clique in these problems is that every node in the congest can only use its small neighborhood, the nodes very close to it, in order to perform this heavy computation of listing. And so we design a long list of very sparsity-aware algorithms so that every node at the end of the day performs an algorithm which is very tailored to the sparsity of its surroundings. And the second pillar upon which your work stands is, well, some form of procrastination. Basically, do what's easy now and do what's hard later on. So we have our work proceeds in iterations, and in every iteration, whenever we see a cluster or an edge which is easy for us to deal with, for example, if we see an edge that we can list all the cliques which that edge appears in very easily, then we do that. And then we solve the easy ones first now, and we throw them out of the graph. And this makes it that if at a certain iteration, some edge or cluster is very difficult to deal with, later on, since the graph will be more sparse, it'll become much easier. And this is the way that we tackle this problem. Now, we invite you to see the full talk for lots of different challenges that come up and the different ways that we solve them and approach this problem. Thank you.
Thank you, Dean. Any questions? We got many compliments on the slides. And I see William has a question. William, would you like to ask it? Orly?
Sure. I just had two questions about the problem statement itself. When you're considering counting, does every node, is it required that every node must know the count or just one node?
Okay, so yes, so in the distributed sense, these problems are local. Or more local. That means that every node just has to output some value, and you require that the sum of all the values is the number. Likewise, with listing, you require that every node just outputs a small list, and the union of all the lists is the entire list of the subgraphs.
I see.
Yes.
Thank you.
Okay, other questions? Okay, so I have one quick question, if I may. So you talk about cliques. How about other subgraphs, say cycles?
Right, so cycles, they've also been studied very extensively, both in so in the congested clique model, it turns out that it really only depends on the number of nodes if you want the tight algorithms and not the sparsity aware ones. In the congest model, it really depends. And you see that, for example, for C4, there's a very, very high lower bound. For odd cycles, it becomes very, very difficult. So cycles is an entire different field. There are lots of works on that, very, very intriguing works. There are also works on trees and other types of subgraphs, yes.
So C4s will be hard, you're saying?
C4 listing in congest, for example, is difficult, yes.
Okay, thanks. Any more questions, or we move on to the next talk? Okay, so seems like we'll move to the next one.
Thank you.
Thank you, Dean. And the next talk is by Sebastian Brandt. And
all right. So
thank you, Sebastian. Please start.
Thanks, Ami. So this is joint work with Alkida Baglio and Dennis Olivetti from University of Freiburg and Yuko Suomala from Aalto University. The question we want to ask in this talk is, how much can we profit from having randomness available in the local model? Which is a question that has been mentioned as one of the most fundamental open problems in the local model by Barenboim and Elkin. And of course, for that question, it's highly relevant what the class of problem is that we want to look at. In today's talk, this will be LCL problems, which are problems that, first of all, are locally checkable, which means that you can define the problem just by defining local constraints. And almost all the problems in the local model that we are interested in are actually locally checkable. For instance, all kinds of coloring problems, MIS, maximal matching, Lover's local lemma, they are all locally checkable. LCL problems on top of that are also only defined on bounded degree graphs, and we also require that in this local constraints, we only use a bounded number of labels. The nice thing about LCL problems is that, well, we know a lot about them, in particular, what complexities they can take on. So if we put this into a picture where we have the deterministic complexity on the x-axis and the randomized on the y-axis, we can now put some dots in here that all correspond to problems with the respective deterministic and randomized complexities. But we do not only know points for which we have problems with the respective complexities, but we also know that almost everywhere else, there is no LCL problem with the respective complexities. So there are only these two white small regions for which we don't know whether there are any LCL problems with those complexities. And for the lower one here, it's conjectured by Chang and Petty that no LCL problem exists in that region. One of the results that lead to these gaps is the result by Chang, Kopelovitz, and Petty that says the randomized complexity of any LCL problem is at least the deterministic complexity of the same LCL problem on instances of size root log n, which for us just means that we cannot profit more than exponentially from randomness. Now we have problems where we profit exponentially from randomness, but all the other problems that for which we know randomized and deterministic complexity are problems where we do not profit at all from randomness. So one big open question here is, are there LCL problems for which we profit from randomness, but only sub-exponentially? And as we show, yes, there are such problems. There are problems that live in this white region here that profit only polynomially from randomness. And in particular, we show that for any positive integer I, there are LCL problems with deterministic complexity log to the I+1 of n, and randomized complexity that is the same, just we have replaced one log n factor by a log n factor. Now, on a very high level, we get these problems by starting with some problem pi0 that has this exponential gap between deterministic and randomized complexity. And then we apply some padding operation to get a new problem pi1, where deterministic and randomized complexity both have increased by a log n factor. And we can apply this process iteratively and in each step get one more log n factor, which will then yield exactly the complexities we want. Now, to give you a idea of what this padding is and how we get a new problem pi1 from a given problem pi0, let's look at what we want to have as our worst case graphs. So our worst case family G is consisting of all the graphs that we get by starting with a root and node graph, roughly root and node graph, and then replacing each node by some gadget, which is just a subgraph that also consists of roughly root and nodes. So in total, we have n nodes, but also the distance between any two edges that leave the gadget is in theta of log n. And then the idea is on these graphs to define our new problem pi1 in a way that is equivalent to solving pi0 on the contracted graph, which will then lead to the observation that the complexity of pi1 on these graphs is just the complexity of pi0 on the initial root and node graphs times the log n factor overhead because each time we want to put communication through a node, we have to spend theta of log n rounds of communication. But well, this is just for the problems in G in our graph class. And then the last step is to extend this to all graphs in a way such that the complexity does not change on graphs in G, but we can show that for all other graphs, we do not get a higher complexity. And that's all I have. Thanks for your attention.
Thank you, Sebastian. Questions? Okay, I see no questions. So if you can unmute yourself today if you have any. If not, I'll thank Sebastian again, and we'll move to the next speaker, which is Pedro Montealegre. Pedro, you're around?
Sure, I'm here. I'm putting my presentation.
Great, thanks.
Can you see my presentation? Can you hear me?
Yes, we see and hear very well. Please go ahead.
Thank you. This is compact distributed certification of planar graphs. It's a joint work with Laurent Feyolet, Pierre Fregnot, Ivan Rapaport, Eric Remila, and Joan Todinka, and myself is Pedro Montealegre. I'm from Universidad Adolfo Ibáñez in Santiago, Chile. So this talk is about planar graphs. Planar graphs are among the most maybe one of the most studied graph classes. And that's because they enable the design of faster algorithms than for general graphs, both for sequential and in the distributed case also. For example, there's this result from Lenzen, Oswald, and Battenhofer from 2008, which shows that a local algorithm for approximation of minimum dominating set, which beats it's in constant rounds, and that beats the log n lower bound for general graphs. And another example is this result from Ghaffari and Heupler in 2016, which shows that in the CONGESTED model, we can compute an MST in order of diameter rounds for a planar graph, that also beats the lower bound of diameter plus square root of n for general graphs. So we aim to avoid performing local computation designed for planar graphs in graphs that are not planar. So we want to certify or be sure that the graph we are working on is planar. So to avoid problems like erroneous outputs or even the lack of termination. So it is known that there are no local decision algorithms for planar graphs, in the sense that there are no algorithms that just looking to the vicinity of a neighbor can decide if the graph is planar or not. So we look to local certification, which is, or more specifically, proof labeling schemes introduced by Koman, Kutten, and Peleg. Here there is an untrustable prover that provides each node with a certificate. The nodes they're allowed to look to the neighborhood and their certificates of their neighborhood, and with that decide if the graph has or not the desired property, in this case planarity. So and the guarantees must be completeness and soundness. This means that if the graph is in the class, then there must exist a labeling of the graph where every node accepts, and if the graph is not in the class, then for every labeling at least one node has to reject. And so our results are first that there is a proof labeling scheme for planarity with certificates of log n bits. Up to our knowledge, this is the first non-trivial algorithm or proof labeling scheme for planarity. And also, as a second result, we show that this is in fact optimal, even for a slightly more powerful kind of local certification, which are local checkable proofs. So there are no local checkable proofs for planarity using certificates of size small o of log n. So well, to show our result, I will explain the upper bound. So we first tackle a specific kind of planar graph that we define as path-outerplanar graph. A path-outerplanar graph is a graph where there is a path that contains all vertices and all the remaining and have a planar embedding where all the remaining edges are above this path. So you have the path, and all the remaining edges go over this path. No edge under this path. We first solve how to certify this class of graphs, and this is very simple. We just give a rank, so a numeration from left to right, and a certification of this enumeration. And also for every edge, we identify that in this kind of graph there is at most one edge over each vertex could be none. And so to each vertex we give which one is this edge above the vertex. And if we give that to every vertex, then the vertices just have to check local consistency, which means that the edge above the two neighbor nodes, it's not crossing essentially. It's more particular than that, but it's roughly that verification. And then we go back we make a transformation from a general graph to a general planar graph to a path-outerplanar graph. So if we have a graph and we take a DFS, and then we define a DFS transversal, which is a tour that starts in the root and visits the nodes in the order of the DFS back and forth. So we start with a DFS. We define that this tour that is the DFS transversal, and then we split the vertices in the number of times that the vertices are visited in this DFS transversal, and then we show that we can connect the remaining edges in a way that the graph remains planar. And with that, the vertices in the tour form this long path, and when we extend this graph, we obtain a path-outerplanar graph. And in fact, this is a characterization. This transformation works if and only if the original graph is planar. So if we started with a planar graph, the obtained graph is path-outerplanar and vice versa. So our proof labeling scheme consists in two parts. First, a certification of this construction, which essentially has to tell each vertex which are its copies, and there is also some details there with how we give all the vertices the information, because one vertex can be divided many times. So I invite you to see my presentation, full presentation, to install those details. And then the second part is the compact certification for path-outerplanar graphs. And all of that we can do it only with log n bits per node. So that roughly explains the upper bounds. And regarding the lower bounds, we show that, in fact, a more general result, we show that any class of graphs defined by forbidding cliques of size greater than 3, or complete bipartite graphs of size at least 4 also require at least log n bits for any proof labeling screen, or for locally checkable proofs, in fact. And that's my presentation. Thank you very much for your attention.
So thanks you, Pedro. Questions? I see Mita with a question, so please go ahead.
Oh yeah, sorry. I realize I can ask the question. Yeah. So the question is simply the checkability model is only by looking at the immediate neighbors, right? Of the.
Yes, only looking to the neighbors, to the immediate neighbors.
Okay. No going further from.
No. Yeah.
Question. Sorry.
Yes. Please.
Hello. Can I ask?
Yes, please.
Yeah. So do you think, I mean, this seems quite interesting, but can you think of any other graph classes for which these techniques, these kinds of distributed certifications might work besides
In fact, we recently, with the same set of authors, we recently extended this result to bounded genus graphs. So
bounded genus graphs. Okay.
Yes.
Right. Interesting. Thank you.
And you can find that in archive if you want.
Thank you. Thank you so much.
Another question, if I may.
Of course.
I didn't get the last bit of what you said, but does it include all this class of graphs for which you prove the lower bound? Does it also include series parallel graphs?
So that's a good question. With precision, what we show that if you have a class of graphs that is defined by a set of forbidden graphs that is cliques or complete bipartite graph, so complete graphs or complete bipartite graphs, we show that you need order of log n bits of certificates.
So it's cliques or complete bipartite or cliques and complete bipartite. That's what I didn't get.
I was said and like a planar.
Like in planar graphs. Okay.
Yes.
Okay. Thank you.
Okay. Thank you very much, Pedro.
No, you don't need both at the same time. You have one or the other. You can have only one or both. It works in both.
Okay, so it includes series parallel graphs. Okay, thank you very much.
Yes. Mm-hmm.
Thank you, Pedro. And we'll move to the next speaker, Christoph.
Yeah, can you hear me?
Yes, we see and hear you. You can put the presentation on full screen and go ahead.
All right, so I'm talking about the distributed complexity of the Lovász-Locke lemma in this joint work together with Sebastian Brandt and Vašek Rosan. So let's start by recalling the Lovász-Locke lemma. There you've given n bad events denoted by E1 up to En, and you assume that the probability that Ei happens is bounded by P, where P is some parameter. Furthermore, you assume that each event depends on at most D other events, where D is an additional parameter. And our theorem by Erdős and Lovász states that if E times P times D plus 1 is at most 1, where E is simply Euler's number, then the probability that one can simultaneously avoid all bad events is strictly greater than 0. And this condition here on the left is also known as the standard LLL criterion. And now that this theorem is only existential, and what we are interested in is also the constructive question. So we want to find a specific realization that avoids all bad events in a distributed setting. So what is the distributed Lovász-Locke lemma? There you associate each bad event with one node in the network graph. And furthermore, you assume that there are independent random variables x1 up to xm. And each bad event depends on some subset of the random variables. And also each random variable only affects some of these bad events. So one can illustrate this by some hypergraph where each of these random variables correspond to one hyperedge. And now again, one assumes that each EI depends on at most the other bad events, where depend in this context means that EI and EJ depend on each other if they depend on a common random variable. And now we're in the local model of distributed computing. That means we consider unbounded messages in synchronous rounds. And also I haven't specified the communication graph yet. And this is illustrated here with the green edges. Namely that there's an edge between two bad events, if and only if they depend on a common random variable. Now the task is to find concrete values for x1 up to xm, such that no bad event happens. And now there's the theorem from 2016, which states that the randomized complexity of the Lovász-Locke lemma is omega log n for the exponential criterion p times 2 to the d is at most 1. Now that this criterion is much stricter than the standard criterion you have seen at the beginning, namely that fewer instances satisfy it. And for the distributed complexity, the lower bound is even omega log n, and it also holds on bounded degree graphs. But there's also some positive result from 2019, and that states that the deterministic complexity is O log star n plus poly d for the exponential criterion p times 2 to the d is strictly less than 1. So note that the two criteria are essentially the same. The only difference is that the less than equal one is replaced by a less than 1. However, there's a small caveat, namely they need to assume Brandtmaus and Ute that each random variable affects at most 3 bad events. And so our contribution in the paper is that we show that this assumption is not necessary. And so from Brandtmaus and Ute, the approach, it also more or less generalizes to when each random variable affects more than 3 bad events. And in the end, the approach reduces to show that all sets in a certain family of sets is convex. And they could only show it for one of the sets in this family, and hence they got this restriction. And so what we do is that we show convexity of each set in the specific family of sets. And so this is also basically our own technical contribution to show that this convexity, which is quite curious for in the area of distributed computing, I would say. And yes, I guess the convexity proof is quite interesting. So it's not just to differentiate something, but I guess it's also does not necessarily have a broader impact in the area of distributed computing. So what are open problems? So one is to find concrete applications for this setting with this quite strict criterion of p times 2 to the d strictly less than 1. So for example, in the setting p times 2 to the d is at most 1, there's the singles orientation problem. Maybe there are also natural problems for the stricter setting. One can definitely, I don't know, construct some problems like hypergraph colorings or so, but I would say so far they're not really supernatural problems. So maybe one can find some application for this. And there are also other problems related to the distributed Lovász local lemma, but there I don't have time to go into detail. So thanks a lot.
Thank you, Christoph. We're open for questions. Okay, so thanks again. No further questions. We'll move to the next speaker, which is
one question. Sorry, one question.
Oh, yes, please.
So on the one hand, you have d plus 1, which is linear in D. The other one you have exponential. What about, between the two criterion in D? Neither. So there,
oh, sorry.
So I mean, the standard Lovász local lemma is E times P times D plus 1 less than equal to 1. So that's linear in D, just purely linear. And here you have exponential in D. Are there also scenarios where it's polynomial in D?
Yes, there also it's also studied criterion where it's polynomial in D. There's also a couple of papers on this, and it's also relevant to some complexity theoretic questions, for example. Yes, so there's, I guess, for this polynomial criterion, I guess there's order poly D log n round algorithm.
Okay.
Randomized, I guess, for example.
Thank you. Thank you. That was it. Thank you.
Okay. So now if there are no further questions, I'll thank Christoph. And we move to the next speaker, Manoj Gupta. Please. Okay, we see you. Can you share your screen, please?
Yeah, 1 second.
Great, please go ahead.
Okay. So the title of my talk is Multiple Source Replacement Path Problem, and this is a joint work with Rahul Jain and Nitish Shamudi. So let's start with the problem. So a replacement path is the shortest path from a source S to a destination T, avoiding an H on the shortest ST path. So as you can see on this picture, there is a path from S to T, and I want to avoid this edge E. So this replacement path leaves the ST path at some point above E and rejoins at some point below T. So this is normally called the D2, which is in green in this picture. So the question is, given an undirected and unweighted graph G and a set of source nodes S, where the number of source nodes is sigma, design an algorithm that finds the length of all replacement paths from each source to each destination node in G. Okay, from all sources to all nodes in the all destination nodes in the G, and the number of destination nodes is n, the number of source node is sigma. If sigma is 1, then this problem is called a single source replacement path problem, which is abbreviated as SSRP. And if sigma is greater than 1, then it is called multiple source replacement path problem. So there are actually a lot of work, but directly related to R, this is a work with Chechik and Kohan in Solar 2019. where they designed a combinatorial algorithm for the SSRP problem, and the running time of that problem was m square root n plus n square. So just to tell you, this n square is kind of necessary because there is a single source, but the number of destinations are n, and the number of edges between the source and the destination is n. So there can be n replacement path between a source and a destination. So the output that this algorithm has to give is itself order n square. So this n square in the running time is kind of forced. Okay. And they have this extra m square root n factor. And they also showed that under a conditional lower bound of Boolean matrix multiplication, no combinatorial algorithm can solve this problem in less than m square root n time. What we have is, we present a combinatorial algorithm for the MSRP problem with the running time of m square root n sigma plus sigma n square. Again, this sigma n square is kind of forced for our problem because there are sigma sources. And like them, we have a lower bound saying that no combinatorial algorithm can do better than m square root n sigma for the MSRP problem under some conditions, conditional lower bounds. So highlights of our result is naturally it works for any number of sources, but there's one more thing. It gives a very, very simple algorithm for the SSRP problem. Okay? Much simpler than the algorithm of Chechik and Koman. And today what I'll do is I'll give a simple observation from our paper that helps in actually getting a simple algorithm for the SSRP problem. So let's look at an edge on an ST path, and I call this edge to be a far edge if its distance from T on the ST path is greater than 2 square root n log n. Now look at the replacement path which is avoiding this edge E. Okay, so this replacement path it moves from S to some point above E, then takes this detour. Okay. So for this P, the suffix of the replacement path P is the suffix of P from the point it leaves the shortest ST path. So for example, in this diagram, the suffix of P is the path which is painted in yellow. Now what I'll do is, I'll generate a random set of vertices which are sampled from G with a probability of log n by square root n. And I'll call these landmark vertices. And I claim that at least one of these landmark vertices is on the suffix of P. Okay, this is because the length of this suffix is actually quite large. It is at least square root n log n roughly. Okay, because E is actually a far edge. Okay, the distance from E to T itself is 2 square root n log n. So you can see in my long talk where I put that there exists a landmark vertex here. Okay. So now if we pre-calculate all the replacement paths from S to all landmark vertices, then I claim that we can also find the shortest path from S to T avoiding E. I'll just use this landmark vertex. How would I use it? Again, I'll not tell, but you can actually use this landmark vertex if you pre-calculate all the replacement paths. But the problem is that even though I know there exists a landmark vertex on suffix of P, I don't know which is that landmark vertex. So what I have to do is I have to process all the landmark vertices and check which one of them is on this suffix. So processing this tuple T comma E, it's finding the replacement path takes tilde square root n time, where tilde hides polylog factor. So this will imply that the running time of my algorithm is n square root n. Why this n square is coming? Because there is only single source, but the number of tuple of T comma E, there are n nodes, and between a source and any destination there might be n edges. So that's why this n square factor is coming, and to process each tuple I take square root n time. And the main problem is how do you get better than n square root n? Okay, I don't want n square root n, I want n square here. Okay, so this is a simple idea which we use. It's pretty simple. What I'll do is for edges that are between the range 2 square root n log n and 4 square root n log n away from D, I'll use a landmark set with sampling probability log n by square root n, like in the previous slides. But for edges which are at a distance of 2 raised to k plus 1 square root n log n and 2 raised to k plus 2 square root n log n away from T, I'll use a landmark vertices with a lower probability, log n by 2 raised to k square root n. Okay, what we show in the paper is for edges which are in this range 2 raised to k square root n log n and 2 raised to k plus 2 square root n log n away from t. Well, you can use this landmark set, and the size of this landmark set is square root n by 2 raised to k. Okay, and using this landmark set, you can actually find the replacement path, and this helps us in improving the running time from n square square root n to order n square. Okay, so this was a simple idea. I didn't go much into it, but more ideas are needed to find the replacement path for edges which are near to t, because currently we are only talking about edges which are away from t, at least square root n log n away from t. So what about edges which are near to t? So we have some other algorithm for that, which is in the longer talk. And if you want to see how we extend our result from SSRP to MSRP problem, then you have to read the paper. Okay, so that's it from me. Thanks.
Okay, thank you. We have time for one quick question, if anyone is interested. Karen?
Yes, I'd like to ask a question. Thanks for the talk. Can you mention which conditional lower bound you use?
So Boolean matrix. Okay, so I think if I actually have this paper with me. So it's Boolean matrix multiplication lower bound. Okay. So this conjecture 27, which says in a word RAM model with words of order log n bits, any combinatorial algorithm for multiplying two Boolean matrices A and B of size n cross n with a total number of m ones requires mn raised to 1 minus small o of 1.5 in expectation.
I see. Okay, thank you. Thanks.
Okay, thank you. And we'll move to the next speaker, which is Yuval Efron.
If you can please.
Yuval, you're welcome to share your slides.
Thank you. Hi. So in this very short talk, I'm going to talk to you about classification of distributed binary labeling problems. This is a joint work with Alkida, Sebastian, Juho, Yannick, Dennis, and Yuka. So, why can I move slides? Oh, okay, good. So in this short talk, my goal is to convince you of the following sentence. That the distributed complexity of homogeneous binary labeling problems on trees is decidable. We are going to very quickly and briefly break this sentence down into its components and understand them one by one. So the first part is distributed complexity. And in this work, we mean the local model of computation, which was already introduced in this session, so I will not elaborate on it. Next, we have binary labeling problems. And intuitively, by binary labeling problems, I mean that given some input graph, we are tasked with labeling its edges either red or blue, such that some radius 1 output neighborhood constraints are satisfied. So for example, in this cute tree here, this is some labeling of the edges by red or blue. Examples of such problems include two coloring, perfect matching, and synchronous orientation. Next, we have homogeneous, which intuitively again means that we don't really care about the output neighborhoods of leaves. By that I mean that leaves don't really care what color was their incident edge given. So for example, in this tree, we would not care about the output neighborhoods of the nodes marked in red. And now I'm getting to our main theorem. What do I mean by decidable? And well, the main theorem is as follows, that the deterministic complexity in the local model of any homogeneous binary labeling problem is one of the following. Either it's O of 1, And then from O of 1, we immediately jump to theta of log n with nothing in between. So in particular, theta of log star n disappears, which is kind of surprising because many natural symmetry breaking problems, such as maximal matching and maximal independent set, are known to admit theta of log star n algorithms, which means that they cannot be represented using only two labels. Then from theta of log n, we immediately jump to theta of n, and lastly, we have unsolvable problems. Furthermore, given the description of a binary labeling problem, we can actually find very, very quickly what both its complexity and what is the optimal algorithm solving it. So to conclude, this was the first step towards automatizing algorithm design for distributed computing. And as open problems, we leave to complete the randomized classification of binary labeling problems and to consider problems with more than two labels. For example, when we allow three labels, already the complexity class theta of log star n appears. For example, the problem of maximal matching. Thank you.
Thank you, Val. Any questions from the audience?
About the work, about life in general.
Many questions about life, but dinner is served in 3 minutes, so we'll move to the next speaker.
Sure,
the answer is always 42, right?
Thank you.
The answer is always 42.
Sorry?
To questions about life, the answer is always 42.
Oh, yes.
I think there are questions in the chat.
Yeah, I know.
Okay, now there arrived one, yes. You can still answer it orally if you want.
Oh, well, it's like implementing it is a bit weird because like only from like reading the description with your eyes, you can already know. Like it's a very simple algorithm. Like you see that the string representing the problem has some very simple pattern, and you can already know what the complexity is and what is the optimal algorithm solving it. If you want more details, you can see the longer talk on YouTube.
The question, just to say, was about the implementation of this classification algorithm. So now I'll thank you, Val, and we'll move to Dennis.
Okay. Do you hear me? Do you see the slides?
Yes, everything is great. Please go ahead.
So I'm Dennis. This talk is about a computer program called Round Eliminator that gives a way to automatically apply the round elimination technique. So let's see what is this technique. So this technique has been used in the last year to prove many interesting lower bounds. So let's see how it works. So we have some problem P0 for which we want to prove a lower bound of t+1 rounds. And the technique works as follows. We try to define a family of problems, P1, P2, up to Pt, such that each problem is at least one round easier than the previous one. And then we prove that the easiest problem of the family, Pt, cannot be solved in 0 rounds. And this directly implies that the original problem P0 cannot be solved in t rounds. So we get a lower bound of t+1 rounds. And and from last year by Sebastian, we know that there is a mechanical way to define this problem family. So given some problem Pi, it's possible to automatically define Pi+1. The problem is that the problem that we get at each step may be exponentially larger than the previous problem. So it's hard to actually do this in practice. And in order to define a large family and prove a large lower bound, we need to do some kind of simplifications to keep the problems small. So now Round Eliminator is a program that does this automatically for us. It's open source, you can find it on GitHub, and you can try it even in your browser. You don't have to install anything. And what it does is it applies this round elimination technique multiple times, and it finds automatically some good simplifications to keep the problems small. So let's just see an example. This is how to encode maximal matching in bipartite graphs, in 4 regular bipartite graphs. So what we can do is just give this problem to Round Eliminator, and what we can do is ask for a lower bound, for an automatic lower bound. So basically we just press a button, automatic lower bound, and what we can see is that the program tells us that this program requires at least 7 rounds. And what I didn't mention is that this round elimination technique can also be used to find upper bounds. So the program does this for us automatically. So we just press a button and we get that this problem requires at most 7 rounds. So what we can do basically is we can automatically know that bipartite maximal matching in 4 regular graphs requires exactly 7 rounds. Now, if we want to prove some more general statement, we have to do it manually, but this can be a good start. Now, you can see the YouTube video to know more about Round Eliminator, but if you want to know more about the technique, there will be a tutorial either today or tomorrow, we still don't know, and we can coordinate on Zulip. So thank you.
Thank you very much, Dennis. It's indeed a very nice line of work. I think 2 other works in this session were about this round elimination technique, so it's worth mentioning. Any questions to Dennis on this? Okay, so I was curious when you talked about upper bounds, in which computational model they are?
Okay, so if you just get an upper bound, it may be that it just works in the local model, but usually the upper bounds that we get actually, I mean, in order to understand the problems, we do simplifications to keep the problems small. And if you get upper bounds in this way, then they actually work in the CONGESTED model, because the number of labels is small and you can actually implement them. You can just run them in the CONGESTED model. So basically you get algorithms for the CONGESTED model also for free.
That's for the upper, and the lower bounds are for...
Lower bounds all in the port numbering model, but we have standard techniques to lift them to the local model actually, also for randomized algorithms.
Okay, thank you. Other questions?
No, just want to say wonderful.
Thank you.
Okay, so if no further questions to Dennis, and I don't see any, I'll thank Dennis and all the speakers of this session, the last for this day, and we'll probably see you tomorrow. Goodbye.
Thank you very much.
Thank you. Goodbye.